So this is Dr. Mohammed Nazam. Good afternoon all to everyone. Great to see you. I'm teaching in Allama Open University, Islamabad, uh, for last 3 years, and has been teaching their different subjects related to analysis, like functional analysis, real analysis, fixed point theory, and complex analysis, differential equations. So there. So it is related to graduate study. Also under some I taught there some undergraduate courses there, and uh, in our university we are offering both distance learning as well as face-to-face study. Uh, in uh, in our faculty of science, we offer face-to-face learning, that is on-campus learning, and the other faculties like education, computer science, and other social sciences, they are offering distance learning coaching. We have a particular pattern uh, which we uses to certify the students in this university. Uh, we have two assignments in the course, and then final examinations, uh, and it is running over the country, and almost in some other countries like Saudi Arabia, UAE. So we are offering degrees there. So, in Faculty of Sciences, I belongs to Mathematics department, and my core area is fixed point theory, which is you can say that a sub area of functional analysis. I have been uh, in touch with this area for over 5 years. I have been span of 5 years of research work in this field, that's fixed point theory. And you can see my Google Scholar link. There you can see my research. I have over 50 publications in this field. This is, in fact, related to existence theorem. That we say that fixed point theorems, and they mostly rely on uh, inequalities. We say that special inequalities, and in the literature we call them contractions. And the research in this field depends uh, on the investigation of such inequalities, and the other spaces, mostly commonly used spaces, are metric spaces. Also, the researchers are generalizing these metric spaces. We have so many other uh, spaces. Different mathematicians have introduced different spaces, like Matthews uh, has introduced partial metric space. It has a connection with computer science, and similarly, Professor Shukla has introduced partial B-metric spaces. Uh, Similarly, Professor Caesarwick has introduced B-metric spaces. I like that. And in my thesis, PhD thesis, I introduced dualistic contractions and ordered dualistic partial metric spaces. And I investigate so many inequalities in that purpose. And uh, uh, I produced around 5 to 10 research papers in this field. However, the work in this field is continuous. People are and mathematicians are investigating different inequalities to get different results. And the most important part of this theory is that it has vast applications. Almost in every field, it has application. It has applications to economics. where we study Nash equilibrium. It has applications to uh, artificial intelligence, the most recent topic and very attractive topic in the research. It has applications to machine learning. It has applications to differential equations, partial differential equations. It has applications to functional equations, matrix equations, integral equations. So this theory has application in almost every field. And in this theory, we produce different fixed point theorem. That is, we model different fixed point theorems to show the existence of the solutions to these equations. And and definitely these equations come from different real model phenomena, real models, real world problems. They are, that they are translated, they are modeled into the differential equations or integral equations or functional equations and extra. And then we need to check their validity, whether the solution of that model exists. So for that purpose, fixed point theory is a good tool, and mathematicians are using it. So we have uh, existence theorem all over the fixed point theory. So here in this talk, I just recall some existence theorem which are from calculus and then which are related to the differential equation and then goes to the fixed point theory. So let's see what is the existence theorem here. As you see, existence theorem is a theorem stating the existence of an object such as the solution to a problem or equation. Generally, the existence theorems are of three types. So in this talk, we will cover all these three types with some known examples. First type is the first type contains existence theorem that give explicit formulas for the solutions. For example, Cramer rules. You see, it's a reference at the below of this slide. So Cramer rules, it is mainly studied in a linear algebra. It is a method that uses determinants to solve system of equations that have same number of equations as variables. It gives a condition for existence of the unique solution to system of linear equations as well as formulas to find the solution. So here is the reference, which is the main paper of the Kramer who introduced this Kramer rules for the system of to solve the system of linear equations. So it's very much applicable theorem. It's very much applicable formula. Okay, it is also it can be applied to solve the system to solve the differential equation. Whereas look at the uh, differential equation one. So if we want to solve this differential equation with the variation of parameters method, then for the second order and the third order differential equations, Cramer rules uh, for the designed particularly for this method is used, where we use determinants. And what kind of determinants? These determinants are known as Wronskians. So here, the existence theorem is that if the Wronskian of the two functions fg is not zero, then one has exactly two linearly independent solutions. These solutions can be worked out by the using Cramer rules. So here, the condition is this: if the Wronskian is non-zero, then there exist two linearly independent solutions. So, and these solutions can be obtained by using the Cramer rules for the second and third order. And above that, Cramer rules does not help there. We have two references for this purpose. Okay. Next type of the existence theorem is the theorems which only state the conditions for the existence of existence of the objects. That is, these theorems, the theorems which fall in the type 2, just only hint at the existence of the object. That is, existence of the solution, existence of some roots. So here we have example of that theorem. For example, Bolzano-Weierstrass theorem. This is the type of existence theorem which falls in the type 2. We have stated here two theorems. You see that every bounded sequence of real numbers has a convergent subsequence. What does it mean? It means it's showing that there exists a convergent subsequence if the given sequence is bounded in the real numbers. So here the condition is bounded sequence of real numbers, and if the given sequence is bounded, then there exists a convergent sequence. So this theorem only shows the existence of the convergent subsequence. Similarly, look at the version 2. Here the condition is that if we have a bounded infinite set, then there exists a limit point. So it shows existence of the limit point here. Okay, you can see these theorems in the two references here. Okay, the very famous theorem in the calculus, it is the intermediate value theorem. It states that if the real valued function f is continuous on the closed interval ab and there exists a number y which is between f of a and f of b, then there exists a number c between a and b such that y is equal to f of c. That is, for every y between f of a and f of b, there exists a number c between a and b which satisfy the equation y is equal to f of c. And the condition is what? F is continuous on the closed intervals. So if f is continuous on the closed interval, then for every y between f of a and f of b, there exists a number c such that y is equal to f of c. So you can see its graph. The continuity of this function directs the graph of this function. You see that, for example, this is a smooth graph. There is no jump. So see that if you take any two finite points and like a and b, and then the graph of the function will run smoothly from a to b. So we can find a point c between a and b whose image always lie on the graph of the function. So this is only due to the continuity at the closed interval. If the function is not continuous, then this is not possible. Similarly, if the interval is not closed, then this is not possible. The next is very important theorem. This is also existence theorem. All these fall in the type 2. Extreme value. Sorry. Okay. Extreme value theorem. The extreme value theorem states that if a real valued function f is continuous on the closed interval, then f must attain a maximum and a minimum value each at least once. So this is also giving us the existence of the theorem. Look at its graph. If we have a closed interval a and b, and the function is continuous, so look at that, the graph runs smoothly. And you see that for every such function having such graph which has no jumps, then you can find, always you can find a maximum and minimum points. It is very clear from the point because the function is continuous, there is no jumps in the graphs, and we have the closed interval. So that's why. Okay. Mean value theorem is most important theorem in the calculus. It has a lot of applications. We'll discuss some of them. What it is, if the real valued function f from the closed interval ab to the real number is differentiable over the open interval ab and continuous at x is equal to a and at x is b, then there exists a number c between a and b such that the derivative of f at c is equal to function's average rate of change over the interval. That is, f dash of c is equal to f of b minus f of a over b minus a. So you see the left hand side represents average rate of change, and the right side is the derivative of the function at the point c. So what it shows it graphically, the theorem guarantees that an arc between two endpoints has a point at which the tangent to the arc is parallel to the secant through its points. Look at its graph. You will be this will be easy to understand this. Look at this. We have a closed interval AB. So this point and this point, these are the endpoints. Look at the red line. So this is the secant line. The red line is the secant line. And we have the curve. Function is continuous. So let's draw the function like that. You can draw, it depends on the value definition of the function. So we just assume that it has a graph like that. Function is graph, there is no jumps. Okay. Okay, we take point C on between the closed interval AB and map it to the capital point C. Okay. We draw the tangent line at C. You see that the tangent line and the chord that is the secant line are parallel because the angle alpha which the secant line makes with the horizontal is equal to the angle alpha which the tangent line makes with the horizontal. So both lines are parallel. So this is the, in fact, basic requirement for the mean value theorem. It always happens. It always happens. When it does not happen, then mean value is not applicable there. Okay, we have some applications here, very important applications which are studied throughout the calculus. For example, how do you prove positive derivative means increasing function? This is with the mean value theorem. With the help of mean value theorem, we are able to say that the function has positive derivative, then it is increasing function. So this is one of the application of mean value theorem. Similarly, how do you prove that derivative 0 on an interval means constant function? Again, with the mean value theorem. Just look at the equation of the mean value theorem. So you get the answer of these results very easily, quickly. Okay, it is the first result which gives an explicit relation between values of f and its derivative. Similarly, curve sketching, the fundamental theorem of calculus, Taylor series, and even L'Hopital rules, they are all redefined versions of the repeated applications of the mean value theorem plus special conditions. So for the assistance, you can click on the links to further read about that. Okay. Another particular or special case of the mean value theorem is the Rolle's theorem. Just put f of a is equal to f of b in the mean value theorem. So you get the Rolle's theorem. And it states that whenever f of a is equal to f of b, then there exists a number c between a and b such that f dash of c is equal to 0. So all these theorems are showing existence of the point. Nothing else. Just imposing some conditions, describe some existence of the point. Okay. Now come to the differential equations. For the solution, for the solution of differential equation, first order differential equation, rather initial value problem, you can say that. Uh, uh, the first theorem, which is a fundamental theorem, is the B2-Existence theorem, which describes the condition for the existence of the solution to ordinary differential equation with some initial conditions. It states that the differential equation uh, bounded initial value bound differential equation has a solution, that is has a unique solution if f is continuous. So if the function is continuous, then it has a solution. However, uh, uh, with reference to the practical problems solutions, it is not as comfortable uh, as the Picard uh, uh, existence theorem. Coming next. So now we have some existence theorems whose proofs involve iteration process in it, and uh, these are put in the type 3. Okay, here in such existence theorems, Lipschitz continuity is very important. Look at that, a function f from R to R, R for real numbers, is called Lipschitz continuous if there exists a positive real number k greater than equal to 0 such that we have the inequality. That is, the difference of the images, the absolute value of the difference of images is less than equal to k times the absolute value of the difference of the points, and it holds for all xy belongs to x. Here, in this case, x is equal to r, the real numbers. Okay. Using the Lipschitz continuous condition or Lipschitz continuity, Picard established a wonderful theorem for the existence of differential equations, that is initial value problems. Look at that. It has several names in the literature. It's known as Picard-Lindelof's theorem, Picard's existence theorem, Cauchy-Lipschitz theorem, or existence and uniqueness theorem. These are all its different names. And what it says, it gives a set of conditions. In fact, it gives us a set of conditions under which an initial value problem has a unique solution. So again, under some conditions, it gives us the existence of the solution. Okay, Lipschitz continuity is a central condition of the Picard-Lindelof theorem, which guarantees the existence and uniqueness of the solution to an initial value problem. Okay, we have reference here. We can for the further readings, you can see that. Now, after the Lipschitz continuity condition, we can go to the Bionic fixed point theorem. Just a little bit modification this. If we just restrict the k between 0 and 1 in the Lipschitz continuity condition, then we just change the name from Lipschitz continuity to the contraction. So a Lipschitz continuous condition will be the contraction if the constant k is restricted between 0 and 1. K maybe 0. So the Bionic fixed point theorem, which is also an existence theorem, it shows the existence of the fixed point, uses Lipschitz continuity with the value of k between 0 and 1. And in the fixed point theory literature, we say it contraction or contractive condition. Both names are contraction or contractive condition. Also, we can say the special inequality. In fact, here we have a special treatment for the inequality. And one more thing here, in the Lipschitz continuous condition, we have absolute value there. That is the difference of two numbers and then under the absolute value notion. But here we also generalize that. that notion. Absolute value notion also generalized in Banach fixed point theorem. Here we develop the metric of the points and the mappings, distance between the mappings, distance between the point. We use the metric here. And this metric is, and you say that the Lipschitz continuity condition is just a particular case of this contraction involving metric. And when we define d of xy is equal to absolute value of x minus y, then we get the Lipschitz continuity, and that is a particular condition. So here we have uh, more generalization. Look at here we have a complete metric space, and in Lipschitz continuity condition, just we have set of real number. So here also we see that generalization, complete metric space. Similarly, the contraction also taken in matrix. And metric can be defined in many ways. So what the Banach fixed point theorem states, it states that if the metric space is complete, then every self-mapping T from X to X, then every self-mapping satisfying the contraction has a unique fixed point in the given metric space, that is in X. So uh, the completeness condition, completeness, you know that a space in which every Cauchy sequence converges is known as complete metric spaces. Okay, so due to the completeness of the metric space, the fixed point converges in the fixed point lies in the given space X. And you know that here, how can we achieve that? The methodology is very simple. We just define a Picard iterative sequence there, and we prove that that Picard iterative sequence satisfying this inequality is the Cauchy sequence. And then using the completeness of the metric space, we prove that that Cauchy sequence converges in that space. And the point of convergence is then proved to the fixed point. Here the fixed point means a point which remains invariant under the mapping. That is t of x is equal to x. If you take any point x from that space, and if you see that t of x is equal to x, then we say that that point is a fixed point. That is the point which is, you say the invariant point, you can say. Okay, it is the fundamental existence theorem in the metric fixed point theory. It appears to be a powerful tool for the existence of the solution of mathematical models involving differential equations and others representing real world phenomena. So it has, as I have discussed before, it has applications in every field, like economics, like computer science, artificial intelligence, and others. So there are fixed point theorems, and we can model a new fixed point theorems uh, to apply for the particular models to show their existence. Okay, now you see that here metric space, in the main players in the Banach fixed point theory are metric space and this contraction. So in the mathematicians working in the fixed point theory uh, works on the metric spaces. Here works on the space. Uh, Metric spaces, they try to generalize that, they try to improve that, and they try to investigate new spaces. And similarly, they work on such type of inequalities. They are generalizing it with reference to different conditions. They are imposing different control functions over this contraction. So, and we have a lot of material in this fixed point. There are hundreds of papers which have been published in this theory, and in very well reputed journals of economics, in others in artificial intelligence journals. in you see that the Springer journals, elsewhere, and many others. So uh, recently, many mathematicians are working in this field, and in fact, it has a flexibility in it. So uh, with some genuine efforts, you can investigate a theorem which can be applicable to uh, new real world phenomena, just to show that it is well defined, or it has the unique solution or not, like in like that purpose. So uh, the work on the existence theorem is on. People are working on it. So uh, you see the people will read for the further reading can look at this paper. It contains information about the Bionic and its results, and you see that it has been published in Bionic General Mathematical Analysis. Okay, I think it's all about my talk. So, uh, thank you very much for this.
Okay, thank you so much, Professor Nazam. Still have a good 5 minutes for questions, so I encourage everybody you're welcome to just unmute yourself, ask a question, or you can put something in the chat and I can repeat it. Um, give everybody a second here. Well, I'm kind of curious. I really enjoyed this kind of overview about existence theorems. I know that I really think it was my first year in graduate school where somebody pointed out to me that existence theorems can be kind of cruel because they don't really often tell you how to find the thing that they claim exists. And I think that was my first time that I had really thought clearly about that. So I'm just wondering, it seems like to me this would be a really good lecture to give to like first year graduate students, to point out to them that there's kind of these different classifications of an existence theorem. Do you give this lecture to your
Uh,
graduate students, or have you thought about it?
in, in fact, it's a totally abstract subject.
Hmm.
So it uses the abstract notions. It uses the notions from uh, analysis. It uses the notion from topology. It uses notions from linear algebra.
Hmm.
So and it comes in the pure mathematics, and it has uh, uh, we cannot see very visible applications,
Hmm.
but the people which are working in existence theorems know that, okay, how can be these theorem model to apply for the different models representing different real world phenomena to show the existence of the solutions. You can see many papers on that, where the particular fixed point theorems or existence theorem are being used to show the solutions of these models. So, in
Hmm.
fact, uh, being these theorems rely on the abstract notions. That's why uh, it look like some maybe for the peoples these are boring, and maybe for the peoples these are difficult, like that. So
Hmm.
there is no uh, maybe the researchers working on that enjoy it, but other people's maybe hesitant to even read that, because what's the existence, where is but you know that people are just um, looking that where is the thing, where is, but
Hmm.
these theorem just show something exists, but where it exists, theorem does theorem is quiet.
Hmm. So there was a question in the chat. Someone has asked, what is your favorite existence theorem?
The Banach fixed point theorem. This is my favorite.
Yes.
because
Yeah.
whole fixed point theory,
Mhm.
the metric fixed point theory relies on that. It was the wonderful theorem given by the Bionic, and uh, I think it changes the direction of the fixed point theory.
Mhm. Mhm. Let's see, more questions. We still have a few more minutes. Well, thank you so much for your talk, Professor Nazam, and it was wonderful for everybody to be here and to get the chance to hear this talk. And let's just thank the
Welcome, welcome.
speaker.
Thank you.
And
Well,
I'm sorry about our first speaker not being here, but we still had a good time here, so I think that was good. And I think the next thing is the closing ceremony, if I'm not mistaken. Um, I'm not sure if that's going to be in the main room. I think, I suppose that's where it'll be. So hopefully we'll see everybody there. Okay, goodbye.